Excellent. Thank you, Veronica. So yeah, welcome to the, I guess, third lecture of the second week, and quantum information in AdS CFT. This is a fairly broad topic. It's seen a lot of activity in many different directions over the past, say, 15 years or so, approximately. And I would say one of the most exciting things is that it doesn't really seem to be a sign of slowing down. So this is a very exciting topic. And I would say the general viewpoint of this course and this topic in general is predicated on the idea that, the very vague idea that natural quantities, whatever that means, in quantum information are dual to nice, again, whatever that means, geometric constructs in the bulk. Now, as currently stated, this is not really a very precise statement, but it conveys the generalization of a particular idea, which has been expressed sort of time and again in holography, which is the idea that entanglement, in some sense or other, builds space-time. So the goal of my lectures this week, and I'll be very happy if I manage to accomplish some part of this goal, is going to be to give a description of some of the entries in the dictionary of quantum information on one side and geometry on the other. And I should say right off the bat, this is far from complete, and it'll most definitely be biased by my own perspectives and my own interests. I will endeavor to spend more time on topics that are the subject of fewer review articles. So because review articles you can sort of more easily find and read, so I'm going to try to focus on things that have fewer reviews written about them. And I'll try to get to some current or very recent developments by the very end. But of course, no promises. We'll sort of see how it goes. I will say one thing, which is that, of course, there's been a lot of very exciting work on the black hole information paradox, and that's related to quantum information in AdS CFT. But you have a whole other set of lectures that's planned on the information paradox. So I will mostly steer clear of the work on the information paradox so that you can see other aspects that you would probably not see in the information paradox lectures. So the most basic sort of fundamental player on the stage for us is going to be the bulk region, so-called the entanglement wedge, which you've all probably heard being talked about. And they're a very, very optimistic estimate, potentially too optimistic. This course is going to have three main components. So the three main components, we'll definitely get to part one and parts of part two, and we'll see how we do with part three. So the first is going to involve defining the entanglement wedge. The second is going to be reconstructing the entanglement wedge, representing the entanglement wedge in terms of the CFT. And the third, which hopefully we'll get to, but I can't make any promises, is complexity and the entanglement wedge. So these are the three main components. Again, we'll start with the definition of the entanglement wedge. As you can see, it's really the key player here. And before we really start with definitions and technical questions, perhaps we should be really asking, given that this entanglement wedge is showing up over and over again, we should be asking ourselves, why is the entanglement wedge so important? And on an intuitive level, it's the answer to a very fundamental question that we might be asking, which is, if quote unquote AdS equals CFT, do subsets of AdS equal subsets of CFT? And the answer is going to turn out to be yes, and this is where the entanglement wedge comes in. So if we want to have an understanding of quantum gravity with AdS boundary conditions via the AdS CFT dictionary, we want to understand the sort of fine-grained aspects of the duality. And so we'd like to understand in what sense do small pieces of AdS get encoded in subsets, subregions, reduced density matrices in the dual CFT. So the definition, the role of the entanglement wedge, it's really about asking the question, how much and which portion of the bulk is encoded in some subset of the asymptotic boundary. And you saw sort of some bits and pieces of this already last week in Mukun's class. So I'm going to review a little bit, just to sort of refresh your memory on some of the constructs that you saw there, and we'll sort of take off from that. So let's suppose that we have some Cauchy slice. So we have our AdS spacetime. We have some Cauchy slice. So let me draw it over here. It's a Cauchy slice of the asymptotic boundary. You can call it sigma, or you can call it partial sigma if you want to think of sigma as the Cauchy slice in the bulk. And we can consider a subregion R on this Cauchy slice. And we're going to define the domain of dependence of this region. Again, it's something that you already saw, but this is just a brief review to jog your memory. So we're going to define the future domain of dependence of the region R. And this doesn't have to be a boundary region. This is just any region in general defining the domain of dependence. This is the set of points P, in this case, that live on the asymptotic boundary, or for defining this for a general spacetime, points that live in the spacetime, such that every path-directed causal curve, meaning time-like or null, or piecewise time-like and piecewise null, through P goes through R. So that's this picture that we often see. You have this region R here, you consider points over here, and they're path-directed time-like or null curves from the point P, and they're going to go through R. And we similarly define the path domain of dependence, which is d minus of R, defined similarly. And then the complete domain of dependence is just going to be the union of those two. So d of R is just d plus of R union d minus of R. Any questions on this? Okay, so let me maybe draw a slightly nicer picture. So we have some Cauchy slice of the asymptotic boundary. We have some region R on it. And so here we have, these represent the asymptotic boundary here. So here we have our domain of dependence on the boundary. So this thing here, this is d of R. Now, once d of R is fixed, R is no longer unique. So this is d of R. This is our R. And once we fix d of R, we could have another slice here, R prime, where d of R is equal to d of R prime. And assuming that you have unitary evolution from one of these slices to the next, then there's no new information that's contained on this slice R prime versus the slice R. Okay, so the question that we want to answer is, if we know all of the data on d of R, meaning we know the state, rho R, So we know everything. So question. We know everything on D of R, meaning we know rho sub R, the reduced density matrix on R, which is going to be given by trace of the complement on some Cauchy slice of your CFT state, which can be pure or mixed. And you have access to all the operators that are localized to D of R, then how much of the bulk can we reconstruct? Now, I have a feeling that if I, put a poll here, I'm going to get the vast majority of you saying you can reconstruct the entanglement wedge, because most likely this is what you've been told. But the entanglement wedge is not the natural thing to reconstruct here at all. The natural thing to reconstruct, the most natural possible object to think of here, is in fact something we call the causal wedge. So if you look at this region, the most natural part of the bulk to be dual to this domain of dependence would be essentially everything, every point where that you can reach in the bulk, say some point here, starting in D of R and ending in D of R by some causal curve. In other words, if you're an observer and you're sort of sitting on the asymptotic boundary and you imagine you holding a flashlight, you fire some light ray in and it bounces off of some point and it bounces back, then, well, that feels like the natural region that you might be sensitive to within D of R. So the natural option, which at this point we know is not correct, but the natural one is the causal wedge. So the causal wedge, which I'll denote WC of R, just the causal wedge of R. This option was proposed by a number of different groups. I'm going to do my best to keep on putting references so you all can look them up, but if I forget, just please let me know. So Busso, Leichenauer, Rosenhaus, Zukowski. So this is a list of authors on one paper, and then also Veronica and Mukund named this the causal wedge in the first place. So that appears to be the natural option. Now, what is the causal wedge? How do we define this object? WCR is the set of points in the bulk, which I'll call M, that can be reached with causal curves that start and end on D of R. And for those relativists in the audience who prefer seeing this in symbols, this is just I'm not going to write it down. This is going to be the intersection of the causal future of D of R with the causal past of D of R. So that is the basic idea behind the causal wedge, and I'm going to draw it. So we have some boundary domain of dependence, D of R, and we're looking at the boundary of the past, and we're looking at the boundary of the future, and there's going to be some surface in here. Wow, this is not a great drawing. And this region here is called WC of R. Now, one distinguishing feature between the causal wedge and what we will eventually call the entanglement wedge, so it's important to sort of keep this in mind anytime we encounter differences, it's important to keep them in mind, is that generically there does not exist a surface H such that the causal wedge is equal to the domain of dependence of the surface H. Generically, this is not true. There are special cases where it is true, but generically, this is not the case. So it will be different for the entanglement wedge, which will literally be defined as a domain of dependence of a surface. All right. So if this were true, if indeed this natural option were the correct option, it would be sort of intuitive, but at the same time would be kind of boring. It would tell us that there's nothing more to AdS CFT beyond the extrapolate dictionary, essentially. So the extrapolate dictionary tells us that if we have some bulk field and we take the limit as we go to the asymptotic boundary, then that allows us to recover, or we can write that down in terms of a local operator into dual CFT. And conversely, we can extend that, as we've already seen in Mukun's class. This can be extended to finite radius by doing a sideways evolution of the equations of motion. So this is the so-called Hkl reconstruction, where we represent a bulk field at a point in terms of some smearing over some kernel, it depends on your geometry, against a boundary operator. So this is the so-called Hkl reconstruction. And the basic idea behind this really is just to specify data on this region over here, and you evolve it into the bulk. Technically speaking, Hkl is not well posed. This is not a well posed boundary value problem. Nonetheless, we seem to think that it typically works. So we usually say, oh, okay, Hkl generally works. I'm happy to talk more with any of you about the problems of Hkl. It's given me many headaches over years now. But as a general rule, it appears to work, even though it kind of frequently has no right to. But the idea is, again, it's similar to with Cauchy evolution, we sort of are able to evolve things starting from some Cauchy slice all the way up to its domain of dependence. And the idea of this is sort of the sideways version of that. And so if the causal wedge were everything that is dual to D of R, then it would essentially tell us that given the causal wedge, you can compute everything about, say, the density matrix rho sub R. And in particular, again, if we're using duality here in a very literal sense, we mean actually dual. I mean, everything that we can compute from rho R, we can compute from the causal wedge of R. Then, so if WCR were really actually dual to rho sub R, then I should be able to compute minus trace rho R log rho R from data that's just in the causal wedge. So this, as you all know, is the von Neumann entropy of rho R. So that would be one thing that we would expect in the case of a duality. I know I can compute this if I know the density matrix, and I can take logarithm of the density matrix, I can compute this. So if in fact D of R is dual to the causal wedge, I should be able to compute this from the causal wedge, from data in the causal wedge. And that turns out to be false. So why is that false?
Netta, could I ask a question about something on this page before you move on?
Absolutely, go for it.
So you said there's no codimension one surface such that the causal wedge is the domain of dependence of that surface?
Generically, sometimes you can find one, but generically,
right. But outside of the vacuum, if you have focusing or something.
Right, yeah.
Is the causal wedge causally complete? Is it its own domain of dependence?
So what happens is if you try to take so this is the causal wedge is defined as in terms of what's in between horizons. And horizons are defined as a congruent that's fired from the asymptotic boundary. And there's a difference between the congruence that's fired from the asymptotic boundary down here to a congruence that's fired from here towards the asymptotic boundary. Because you get conjugate points in different directions.
Sure. On these horizons, you'll have positive expansion going towards the boundary.
Yes.
But is that only a problem? I guess what I'm asking is that only a problem of codimension? Like, is D of WC equal to WC?
No, it's not. It's generically not. No.
Does it gets bigger, I guess?
It gets bigger. That's right.
I would think the problem would be that it would get. Oh, okay. Great, I see. Thank you.
It gains extra space. So the causal wedge law
Right.
was included inside of a domain of dependence, but it
Right.
in of itself is not its own domain of dependence. Yeah.
Thank you.
Other questions?
Yeah, can I ask something that, well, it might be a bit of a historical question, but ever a puzzle that the causal wedge of the entire boundary sometimes does not include the full geometry?
Yeah, so certainly, for example, if we were looking at Vidia, for instance, so any black hole really, whenever you have a black hole, but it's easy to see this for Vidia, AdS Vidia. So in this situation, of course, the causal wedge is everything in here. And historically, indeed, there was a lot of debate about whether the black hole interior is even encoded in the dual CFT at all. So because again, the causal wedge just seems like such a natural thing to be dual to the CFT. And with HKLL in hand, there would also seem that we have an explicit construction of it. So, so what could we really be missing? Well, maybe just the black hole interior is just not part of the AdS CFT dictionary. And fortunately, very fortunately for us, that turned out to be false. AdS CFT would be kind of boring if that were true. Other questions? Okay, so okay, so we were just about to explain why it's false that that the causal wedge is dual to d of r. Now there are many different ways in which we could go about explaining that, but one of the ones that I sort of find most well motivated is the fact that the von Neumann entropy. So let me write it down again: S of rho r equals minus trace rho r log rho r. So this we can actually just write this as minus the expectation value of log rho r in this state rho r. And this is taking a logarithm of an operator is a very non-local thing to do. And so we don't expect that this is something we can sort of generically nicely compute just using local operators, but we can actually reconstruct the causal wedge just using local operators. And local operators on d of r. And so already that seems to suggest that we may have a problem if we want to say that there's a duality between the causal wedge and the entanglement and d of r. And at the same time, we don't seem to be able to compute this quantity here because the causal wedge does appear to be reconstructible from these local operators using HKLL. So what is the actual duality? Now, I wanted to say a few words about properties of the von Neumann entropy, but maybe let me first, let's see, don't want to do it this way. Okay, let me first mention an open question and then I'll move on to that. So, so one thing which we figured out now is that it's really the entanglement wedge that's important, but it's actually still an open question. What is the role of the causal wedge in AdS CFT? So an open question for any of you to think about is what is the dual specifically of the area of what we call the causal surface, which is the rim, the edge of the causal wedge? What is the information theoretic dual of the causal wedge? There's been some of WCR. So there's been some progress on this from the perspective of complexity, computational complexity. And I will try to say a few words about that at the very end, but it is not, progress is not the same as answering this question. This is still very much an open question, an open problem. So I wanted to say a few words about the von Neumann entropy, since as you probably know, it's going to be critical to the story. Now, I'm not going to encroach too much on Horacio's territory here, but I do want to say just a couple of things that will be important for us. So a few comments, since clearly the von Neumann entropy was something that we used to argue that the causal wedge is not the dual of d of r. So I want to say a few words about the von Neumann entropy and how it's going to help us figure out what the actual dual is. So a few comments on SVN of rho r. If I switch back and forth between S and SVN, I'm sorry about that. It's kind of habit at this point to equate them to the same thing. So if you're not sure what kind of entropy I'm talking about, just let me know and I'll clarify. It's 99% of the time it's going to be the von Neumann entropy. So a few comments on that, a few points I just want to make. So one thing I already said is that this is something that we think of as non-local. It's the expectation value of a non-local operator, logarithm of an operator. It's also UV divergent. This is something that you've already discussed in previous lectures. So we typically regulate this several different ways. The main regularization scheme that I'll be using here is going to be inserting a UV cutoff. So a cutoff at very short distances. This is very natural from the perspective of AdS CFT and this so-called UVIR correspondence in AdS CFT. So typically that's what I will be using here. And the leading order divergence with this type of UV cutoff is proportional to the area of the surface whose entropy you're computing. So if we have some surface and it has some area, let's call this surface sigma, then we expect that there's the leading order divergence, at least in higher dimensions, is going to be area over the cutoff to the to d-2, and has a logarithmic divergence, which you already discussed today. When you're in 2 dimensions, really in odd dimensions, you'll always have some subleading UV divergence. Another important point for us is that if the entire system, rho r union r bar, so here this means complement, is in a pure state, then S of rho equals 0, and S of rho r is going to be equal to S of rho r bar. So that's only for a pure state. So you have pure state on the entire Cauchy slice of the asymptotic boundary. And another comment we have, so this, maybe I'll make this, so this is not a minus sign, this is a little bullet point. We have the von Neumann entropy satisfies strong subadditivity. So you have 3 subsystems, A, B, and C. So typically when we have one subsystem, I'll just use R. When we have multiple ones, I'll use A, B, C, and so on. So S of rho ABC plus S of rho C is going to be less than or equal to S of rho AC plus S of rho BC. And finally, one final important point for us is regarding different Cauchy slices of the same domain of dependence. As long as we have unitary time evolution that takes us from R to R prime within our domain of dependence, then S of rho R will equal S of rho R prime. More generally, sorry, I can't see this. More generally, whenever you act with a unitary on D of R, a unitary that's localized to D of R, that will not change the von Neumann entropy of rho R. So are there any questions on these sort of lightning review of properties of the von Neumann entropy? Questions? Okay. So talk about the causal wedge. Okay, so now we have our motivation. The natural quantity, the causal wedge, is not what we want it to be. That's not the dual, and it's time to find the dual. And so we are going to go about defining the entanglement wedge by first talking about how we compute the von Neumann entropy of the density matrix rho sub r. So we'll first discuss a sort of brief motivation from black hole thermodynamics, and then actually the so-called Ryuta-Kiyanagi prescription, which is the way of computing von Neumann entropies for whenever your bulk spacetime is static, no time dependence, and whenever you're actually computing it, and it's purely classical. So that's going to be important. So let's begin with a little bit of motivations. This is sort of, now that we're done with the preamble, this is part 1 of the lecture, which is about already half an hour into the lecture. So this is sort of, I like to think of this as V0 of holographic entanglement entropy. Graphic EE, which is due to Bekenstein and Hawking. So I imagine that some of you have probably heard of the so-called Wheeler-Gedanken experiment, and maybe you've seen me give a talk on it, or maybe you've seen others talk about it. The basic idea is roughly, you say the following. So this was actually a problem that Wheeler gave to his student at the time, Jacob Bekenstein. So, you know, this is the kind of problem that you can expect to solve if Wheeler is your PhD advisor. So basically, the idea is the following: black holes, if black holes have no microstates in classical gravity, then, well, they have no entropy in classical gravity if they have no microstates, which means you can sort of take arbitrarily large amounts of matter, which certainly has entropy. You can throw that matter into the black hole, and you can decrease the entropy of the universe by sort of arbitrarily large amounts. You can keep on decreasing the entropy of the universe in gross violation of the second law of thermodynamics. And then Wheeler said to Bekenstein, you know, solve this problem for me. This irks me. And you know, Bekenstein solved this problem, which is really impressive. And he said, okay, black holes actually do have microstates. The microstates due to quantum gravity, and the entropy of a black hole as a result of these microstates is proportional to the area of the event horizon over 4G. And typically, I'll omit the H bar. You can write, this would be GH bar here, but we usually just set H bar to 1. And you know, really, it's a miraculous discovery, and what's almost more miraculous than the discovery itself is the fact that you can think of this as the black hole entropy, or you can think of this as the Bekenstein-Hawking entropy, and the acronym doesn't change, which is kind of fantastic. So then, this was Bekenstein's idea, so why is it called the Bekenstein-Hawking entropy? Well, Hawking subsequently computed the temperature of a black hole, and that gave us the proportionality constant for this, which is the 4 here. So I guess they should have said this is just proportional to area over G. And Hawking's calculation of temperature, which then we plug in for the entropy, told us this is actually the number 4. And this was really a monumental discovery. And in an incredibly impressive paper in 1995, Strominger and Vafa actually gave a microstate counting argument for this formula in 5-dimensional extremal Reiser-Nordstrom. So this was specific to that black hole, but that program has expanded since. And that has given us very good evidence that this formula is genuinely coming from quantum gravity microstates, and that is genuinely the entropy of a black hole. Now, I like to think of this as version 0 of the complete formula for the entropy that's associated to a region or subregion of a gravitational system. So in some sense, this is the sort of beginning of entropy in gravity. You can sort of trace it back, in my opinion, at least, to these developments in black hole thermodynamics. Now you might say, well, wait a minute. Area of the event horizon, that sounds like the causal surface to me. That sounds like the causal wedge to me, right? The causal wedge is the region that, you know, if you're, let me draw a picture here, again, of idea, even though they probably had asymptotically flat black holes in mind. So you say, well, okay, what's the region where I can, if I'm an observer, I can sort of both receive light rays from the asymptotic boundary and still send light rays to the asymptotic boundary. That's what the causal surface, the causal wedge is. And so if you're sort of an observer sitting right here, well, certainly I can receive signals from the asymptotic boundary, and I can send signals to the asymptotic boundary. And if I'm over here, well, I can still get light rays from the asymptotic boundary, but I cannot send them. So this is the causal wedge. And so you say, well, the area of the event horizon, that sounds like causal wedge related. That sounds like assigning an information theoretic quantity to the causal wedge. And you just told us that we don't know how to do that. So, you know, what happened? Did they already solve this problem in the 70s and you're just lying to us? And the answer is no. I'm not lying to you. This is a very special case where the causal and entanglement wedges coincide. So we'll talk a lot more about this. So, you know, not this case, this is, so in a stationary black hole, stationary space-time black hole, the causal wedge of the entire boundary is equal to, again, we haven't defined this beast yet, but we will, to the entanglement wedge of the entire boundary. It's one of these really non-generic cases where the causal and entanglement wedges coincide. And in fact, what's kind of fascinating is that in this very recent development, so in a paper with Jeff Pennington and Arvind Shabazzi-Magadam, we actually showed that the causal and entanglement wedges coincide if and only if log of rho r is an integral of a local operator. So there's a locality comes back to strike again. So, and that's a very, very non-generic thing to happen. So it just happens to work out so that in this case, you know, they're the same, so we don't have to worry about the distinction. But we will have to worry about the distinction already when we're talking about classical static spacetimes, if we choose sort of non-trivial boundary subregions. So with that, we will move on to part 2. So part 1 was actually quite short. Part 2 will be significantly less short. So part 2 of the lecture, that's what I like to call version 1 of holographic entanglement entropy. So this is S of rho r for classical static AdS duals. I should first pause here and ask if there are questions, actually.
Yeah, I had a question.
Go for it.
So how do the corrections come into the corrections to the black hole entropy? How do those come into the interpretation of there being like the causal wedge and all that?
So when you say corrections, do you mean quantum corrections, or if you perturb it, then dynamics, or what kind of corrections do you mean?
Quantum corrections. Like
Quantum
last
corrections.
week we learned that in the Strominger-Vafa calculation, it's, you know, the whole walled formula.
Yeah, that's an excellent question, and I'm going to have to ask you to hold on to that question for until maybe late in the lecture tomorrow, or maybe even the day after that. We are going to spend quite a while talking about quantum corrections to this formula, and that will also, then we'll also discuss Bekenstein's idea about how to correct his formula for quantum corrections. So we will certainly talk about that, but for now we're only going to worry about classical spacetimes, meaning we're going to not even consider any kind of quantum fluctuations whatsoever. No back reaction, no quantum fields, everything's classical for now.
Okay, sweet.
I think Naomi was also referring to like alpha prime higher curvature corrections.
No higher
in the
curvature,
classical
no
form.
higher derivative. We are talking about, you know, your friendly Einstein gravity theory that doesn't have anything exotic in it. We will discuss all of the, so right now, my current plan is that we'll have versions 1, 2, 3, 4 for, you know, every single time we're going to add more corrections until we get the sort of final formula. And then we'll go from there to actually, that'll be the final definition of the entanglement wedge. And then we'll go from there to talk about reconstructing the wedge. So patience. Other questions?
Yeah, one other
Yeah.
question. If you could repeat the necessary and sufficient condition to have then causal wedge to be equal to the entanglement wedge.
Sure. So in order to have the entanglement wedge and the causal wedge be identical to one another, this is true if and only if the so-called modular Hamiltonian, so the log of or minus log of rho r is the integral of a local operator, which is another way of saying that. So it generates a local geometric flow. If you think of sort of flowing things along using this sort of this quantity, which we call the modular Hamiltonian. And if you want to see the proof for that, that's a paper that I wrote with Jeff Pennington and Arvind Shabazzi-Magadam. It's not our most recent paper; it's the one before that.
Very much.
Other questions? All right, if there are no other questions, then we will move on. Okay, so let's consider now a space-time with no time dependence. So static, and it has no quantum corrections, classical. And classical here, I also mean no classical stringy corrections, no alpha prime corrections. Again, we're just talking about very standard Einstein gravity as far as the theory goes. Now, what I mean by static here is that there exists a time-like vector field. So I'm just going to draw a bunch of Cauchy slices here. So that means we have a foliation by these Cauchy slices, and there is a globally time-like vector field called TA. So this, just to label this T here. So there's a globally time-like killing vector field TA, which is normal to the foliation by these slices sigma T. So that's what I mean when I say static. Now, I don't know if there are any picky relativists in the audience who will tell me, how can this possibly be a Cauchy slice? AdS is not globally hyperbolic. And yes, this is true. Technically speaking, a Cauchy slice or any one of these will have, we'll look at this thing here, and it'll have some domain of dependence, and that will certainly not be the entire asymptotic boundary, so the entire space-time. If you're not a relativist and you're not worrying about this, then please keep on not worrying about it. But if you are a relativist and this is sort of keeping you up at night, then the way that we solve this problem is we just say, oh, just include the asymptotic boundary in your definition of the Cauchy slice when you take the domain of dependence. So what we mean is we say, okay, technically speaking, these are what are called AdS Cauchy slices rather than Cauchy slices. And what we mean by that is if you take the domain of dependence of sigma T union, its boundary, where this dot here means the asymptotic boundary. So here we're working the so-called conformal completion, that this is actually gives you your entire space-time. So this is what we mean by AdS Cauchy. I'm just going to call them Cauchy slices for all intents and purposes, unless you're trying to prove some singularity theorems in AdS. This is good enough. It turns out that even if you want to prove singularity theorems in AdS, this is almost good enough, and just have to go through a little painful exercise of taking the conformal completion, untaking the conformal completion, and taking it again. But we're not going to be proving singularity theorems in AdS, so it's not relevant for us. Questions on this? Okay, so that's our setup. Yeah, question.
Yeah, just a clarification about exactly what you mean by including the asymptotic boundary in order to define what the Cauchy slice. Like, do you include a set of boundary conditions for the
Yes, absolutely. You mean you put in your boundary conditions, and that means that basically this is globally hyperbolic, meaning that you have a deterministic evolution of initial data, but you actually don't unless you also supply initial data at the asymptotic boundary. So what we're saying here by sort of AdS hyperbolicity is that if you supply initial data both on a Cauchy slice and on the asymptotic boundary, then you have a complete deterministic evolution. Other questions? Okay.
Sorry, I have a question. You've written this sigma T dot in the second
Yes.
term. Do you supply the boundary conditions in the boundary for all time or for just one particular time?
You have to specify it for all time. Now, that can also mean specifying it at one time and then saying that your CFT evolves in a particular way. And then that's enough to specify.
But then you're specifying a Hamiltonian for the CFT.
Precisely, yes.
Okay.
Yeah.
Thank you.
Other questions? Okay, great. Okay, so just an example of something of what we mean by static spacetime. So we have AdS Schwarzschild. The exterior of AdS Schwarzschild is static. That's sort of a canonical thing to work with when we're talking about this static proposal. So here we have AdS Schwarzschild. It's really just the outside of it that's static. And the time-like vector field is essentially just a boost generator. So here we have some slices of this. So, and we have some, essentially it's a boost generator here, and that's the time-like vector field we're interested in. And of course, you can also extend these into the other side. And the same boost generator will be moving backwards over here, just like it does in Rindler space for when you're doing this decomposition in Minkowski space. Okay, so in this setup, Rie and Takenagi, who were the ones who proposed this, noted that if you take a Cauchy slice of the exterior, so draw it over here, So take a Cauchy slice of the exterior. So here's the event horizon. There are two asymptotic regions. Then the area of the event horizon is a local minimum of the, so the event horizon is a local minimum of the area functional. So think of the area functional here is the induced metric on this, and I'll write down a slightly more precise version of that in just a moment. But H here is the metric on this bifurcation surface. And what they noted is that this is a locally local minimum of the area functional. So this here is the induced metric on a codimension 2 surface. So let me be a little bit more precise here. I'm going to draw a somewhat more convenient Cauchy slice, but this is just for illustrative purposes. So suppose we have some Cauchy slice, and we have some surface sigma on it. Then sigma is codimension 2 or d minus 2 dimensional. Use those interchangeably. That means that, well, it's got two linearly independent normal vectors. And we can say, well, let's take one of them to lie on my Cauchy slice. And I can take the other to be the same as the one that's normal to the Cauchy slice. And that allows me then to write down an induced metric. So HAB. So this is JAB, which is the metric in this space-time, plus TATB minus NA NB, where these are normalized to -1 for T and +1 for N. So this is the metric on the surface as induced by the ambient geometry. Now this is just one choice of a decomposition of the space of vectors that's normal to sigma. We can also say pick, two null vectors, KA and LA, and we could just as easily write down GAB plus LAKB plus LBKA, and here I've normalized things so that LAKA is -1. So this is what I mean here when I write down this. This is the square root of the determinant. This is the infinitesimal area element. Taking the integral over the surface gives you the complete gives you the area of the surface. So one sort of suggested exercise to do is to show that the bifurcation surface of Schwarzschild AdS is a local minimum of the area on a static slice. And when I say static slice, just to be clear, I mean one of these slices that we get from that are normal to this vector field TA, okay, which is a killing vector field. Because you could, take another Cauchy slice and sort of wiggle it around, or you could even take a piecewise null Cauchy slice. But here, when I say a static slice, I mean one that's a member of this preferred foliation. So useful exercise to do if you want to sort of see this at work. Now, the bifurcation surface of Schwarzschild is, of course, not a global minimum of the area functional. Anybody want to tell me what the global minimum of the area functional is? Any thoughts? How about the empty set? That seems to have area 0. So maybe, we're looking for some local minimum of the area functional, but apparently we're not looking for a global minimum of the area functional. So how do we navigate this particular hurdle? And the difference between the empty set and the bifurcation surface of the event horizon is that the empty set is not quote unquote homologous to the asymptotic boundary. And so in particular, does not exist a hypersurface H. Hypersurface here, I mean D minus 1 dimensional or codimension 1, such that the boundary of H dot is going to be equal to the union of the empty set, or I guess let me put it this way, such that H is H connects, I'll put the correct definition in the precise definition in a moment, H connects the empty set to the asymptotic boundary scry. And what I mean by that is, in particular, what we're going to demand, a so-called homology constraint, is that there exists, so this is called the homology constraint. So we'll say that X, and there is a different definition of homology in the math literature, which is more precise, which I suspect is related to this one, but it's not entirely immediately obvious exactly how to map one to the other. That was in terms of simplices, and this one is sort of just in terms of surfaces. That one required signed volumes, and this one doesn't. I suspect they're really the same thing at the end of the day, but nobody's worked out the details as far as I know. So what we're going to call this a homology constraint, because that's what we do in the literature. So X is homologous to scry, and more generally, XR is homologous to R, but I'll say that in just a second. If there exists, let me just do it already over here. R is homologous to R. If there exists a hypersurface H, and we really require this hypersurface to be space-like, such that H dot, the boundary of H, is X union R. And in particular, there is no such surface for the empty set, as long as we're considering just one asymptotic boundary. So if we're just considering one asymptotic boundary, there's no surface that does this, because if you take a look at this Cauchy slice here, the empty set will give us the complete Cauchy slice, and that one has this boundary also. And so that tells us that this is the minimal area surface that's homologous to one boundary here. And this finally gives us all the ingredients we need to state the so-called Ryu-Takenagi proposal. So I'll keep the definition of the homology constraint here. Okay, so SBN of rho R for static bulk leading order in G Newton. And this is due to Ryu and Takenagi. So let R be a boundary subregion on sigma dot T. So this is a Cauchy slice of the asymptotic boundary. And in particular, it also is the intersection of one of these nice preferred foliation slices with that of the asymptotic boundary. So it's not just any Cauchy slice of the asymptotic boundary, it's one of these preferred ones that we inherit from the bulk. So let R be a subregion of that. Then S of rho R is equal to the area of XR over 4G, H bar if you want to include H bar. And again, this is to leading order in G, where XR is the minimal area surface on a static, or on the static slice, sigma T, which is homologous to R. And this homology constraint is really crucial. Otherwise, we just always have the empty set here.
Hi, sorry, could you just repeat the first line, please?
The first line, so that R be a boundary subregion.
No, it's for a static bulk.
Oh, to leading
What's the next word?
order in
Okay,
in G
thank you.
Newton.
Okay.
Yeah. So there will be higher order corrections here, and this is also to leading order in alpha prime if you want to do string theory. So this is basically to leading order in everything and ignoring any time dependence. And I know that this might seem like a really sort of a baby step thing to do, ignoring any potential complications. But I want to emphasize this is actually a tremendous advance, this idea that the Bekenstein-Hawking entropy could be applied to boundary subregions, something that's anchored to the boundary, something that's not the event horizon of a black hole. This is really incredibly insightful. So just because it applies to this very restricted set of spacetimes doesn't take away from how insightful and important this advance is. So are there any questions on this statement of the Ryo-Takayanagi? Yeah, go for it.
So before this, everything that you did would have worked for any GR geometries, but this is the first very AdS thing to do because it requires the boundary. Is that right? So everything before this could have been done for even, say, flat spacetimes?
When you say everything before this, do you mean the Bekenstein-Hawking?
So let's say the Bekenstein-Hawking entropy and
Sure.
The causal wedge.
Absolutely, yeah. So all of that could have been defined. I mean, okay, not every spacetime even has an asymptotic boundary. So, if you don't have an asymptotic boundary, I don't know how you define the causal wedge. You could define that if you have a asymptotic. So if I had, for example, a closed recollapsing universe, so North Pole, South Pole, there's no asymptotic boundary here. And I don't know how to define the causal wedge here of anything because there's no asymptotic boundary, there's nothing. So not everything would have worked for any space-time. And you can also fight about what you mean by, in de Sitter for de Sitter type space-time. But if you have it, yeah, go ahead, Veronica.
Even in asymptotically flat spacetime, you can't really define a non-trivial, boundary domain of dependence.
Yeah, so exactly. So I would say in asymptotically flat spacetimes, it's a little difficult because it's not the same. Yeah, as Veronica says, it's a little. Conceptually, I'm not entirely sure what how would think about the causal wedge, given that you sort of have to include I naught in any kind of causal wedge you want to define. So it's not really going to be the domain of dependence of a subregion. So in some sense, it really is an AdS construct, the causal wedge. And I would say the entanglement wedge also, although the entanglement wedge in some sense is more easily generalized if you just allow yourself to pick arbitrary regions.
Thank you.
Other questions? All right. Okay, so let's take a look. Just have a picture here of what this might look like. So here we're looking at a slice of AdS and pick a boundary subregion. And we expect that the surface will actually want to hang into the bulk. They want to go in rather than stay close to the asymptotic boundary because of the AdS warp factor. So because of the AdS warp factor, areas get smaller as you go deeper into the bulk. So it's advantageous for this surface to want to go deeper in. If we had something different, if it were less advantageous for areas to get smaller, then this might not be super well defined. If it were advantageous for it to stick close to the boundary, then you say, well, I guess we're sort of out of luck. This thing is just always going to lie on the boundary. But fortunately, that's not what happens. We have this interesting wedge. I am using that word purposely. There's an interesting sort of wedge shape. Well, it's not a wedge yet, but there's an interesting region here, and this is non-trivial, this surface. So I want to make a few comments on Ryo-Takayanagi, and probably will not get to make all of them today, so then we'll make some of them tomorrow. So some comments, some remarks. I've yet to figure out why journals allow you to sometimes make comments and sometimes make remarks, but they're very particular about whether something is a comment or a remark. So if any of you ever figure that out, please let me know. So I'm going to call these remarks based on my many years of dealing with journals and deciding that this qualifies as a remark. Guess you develop that kind of intuition eventually. All right, remark one. Formally, this is infinite on both sides. So let me write it again. We have S of rho r equals area of XR over 4G. Now, again, this is formally infinite on both sides here. So we already know, that this thing here, this is UV divergent. So for example, for a 2D CFT, S of rho r equals C over 3 log of the interval length over epsilon, where epsilon is the short distance UV cutoff. And in AdS3 CFT2, C is inversely proportional to G Newton. So in the large C, or equivalently small g limit, GH bar goes to 0 limits of the classical limit, we have, in some sense, you could say, oh, we could have like two divergences, right? We have the, we have the thing that's coming from C here. This is a large central charge. So this is very large here, and this is very small. So this quantity is also going to be divergent. And similarly, we have two similar properties here. We are in the GH bar goes to 0 limit. So we have this thing that's going to 0. But the area of this is also formally infinite because, well, it goes all the way to R goes to infinity. So the area is going to be infinite. So in some sense, you could say, well, in what sense does this formula even make sense? It's just infinity equals infinity. And that's not really ever going to be false unless the infinities are of a different cardinality. So sort of what are you worrying about here? But the non-trivial thing is that when you regulate this divergence by, say, putting a UV cutoff over here, well, in the bulk, that's going to correspond via UV-IR correspondence to a large radial cutoff. So in fact, we cut this off in global AdS coordinates at R goes as 1 over epsilon. And so the area is very large and it is, divergent as R goes to infinity, but we have this cutoff 1 over epsilon. And what's, of course, miraculous, fascinating, exciting is that these cutoffs exactly appear to match up. So that the divergence in the area due to this thing going all the way to the asymptotic boundary is balanced out by has the same behavior as the UV cutoff in the CFT. And so there's a very non-trivial sense in which these do actually compute the same thing. It's not just infinity equals infinity. When we regulate it, when we cut it off, and we look for the universal component, they really do match up. So that's of course a very non-trivial check of Ryu Takenagi. Are there questions on that? No questions on the UV-IR correspondence? Everyone's on board? Okay, maybe a couple of exercises before we move on to remark 2. So, and by the way, if you don't manage to write down quickly these exercises that I'm jotting down, I will post these notes on the TOSI wiki, so you'll be able to sort of see this and work on it on your own time if you'd like. So one thing that you can show, not too much work, is show that the minimal surface on a static interval in pure AdS3 is a space-like geodesic. Now, this will turn out to be much more general than just static spacetimes, but for now, static spacetimes is the game we're playing, so we're going to stick with the static case. And the next thing to do, which is not very hard once you've done that, is to reproduce the equation for S of rho R in a 2D CFT from the length of the space-like geodesic. Of course, we typically talk about area, but here the bulk is 2 + 1 dimensional. So you could still call it area, but it's a little funny. So, it's really just a length. It's the element of a codimension 2 surface. It just happens to be a line in 3 space-time dimensions. Now, let's move on to our second remark, unless there are questions. Alyssa, there are lots of questions. Yeah. Mm-hmm.
Oh, can I just ask a question about the first
Certainly.
exercise you wrote there?
Yes.
What exactly do you mean? I thought that was sort of the definition.
Well, okay, but this essentially boils down to is writing down the area functional and varying it and reproducing the geodesic equation. So it's something that you've
Okay.
probably done in your undergraduate GR class. It's just typically we don't talk about space-like geodesics. And I know that in grad and undergrad GR classes, we almost never worry about what the space-like geodesic is doing. So it's kind of valuable to just see the behavior of a space-like geodesic. There's also a somewhat non-trivial thing here, which is that technically speaking, the geodesic equation is not well posed as a boundary value problem. That means that you can have either no solutions or multiple solutions given a set of boundary conditions. It's a well-posed initial value problem, which means if you supply the initial point and the tangent vector, you're guaranteed a solution, and a unique solution. But here we're looking for a boundary value problem. So it's not quite as trivial as it sounds it's not always as trivial as it sounds to solve for these geodesics, and you'll often find more than one satisfying your boundary conditions. In that case, you have to find the minimal one of all of the ones that you get.
Cool.
And this is a sort of, in some sense, a trivial exercise. It's kind of just getting your hands dirty with working with space-like rather than time-like or null geodesics. Other questions? Okay, remark 2. For Schwarzschild AdS, it is in fact, shocker, the bifurcation surface. So the locally minimal surface, we already talked about this, but you can sort of do it out yourself. The locally minimal surface for Schwarzschild AdS, one boundary is the bifurcation surface and for two boundaries, it's the empty set. That tells us, okay, for two boundaries, we have a pure state because the von Neumann entropy will be 0. But for one boundary, we have a mixed state because the von Neumann entropy is non-zero, and therefore the CFT cannot be in a pure state. And you can sort of already start to see now a connection between von Neumann entropy and space-time, or building space-time, where you say, okay, well, the von Neumann entropy of the entire thing is 0, but the von Neumann entropy of just one side is non-zero, which suggests that there's something else there. If the bifurcation surface is non-empty, then there's something non-trivial topologically behind it. So this is not very precise, and we will make it more precise, but it's sort of a hint that you're already starting to get at seeing how, the existence of additional geometry is in some sense related to the entanglement. And don't worry if this seems like a vague, fuzzy concept right now, because we really haven't made it precise yet. But that is in some sense where we're going. That is in a large sense where we're going in the next few days.
Can I ask a quick question?
For sure.
So when you say two boundaries, do you mean a boundary and its complementary region in the boundary?
I mean the complete, so here, very good question. Let me draw a picture. So here's a Cauchy slice of AdS Schwarzschild. And I mean the full Cauchy slice and this full Cauchy slice. So I'm not talking about a boundary subregion. I'm talking about the full region, the full asymptotic boundary on both sides, as opposed to the full asymptotic boundary on just one side, because you have two components to the asymptotic boundary. Does that make sense?
Thank you.
Netta, you have 5 minutes left.
Great, thanks, Veronica.
Hi, sorry.
Right, sorry.
Sorry, other question?
Yeah, I have a question. I was asking if the idea here is that if you have both the boundaries, you have a pure state, like the TFD, for example, and that's why you have real Taganagi gives you an empty set, and so it's zero entropy. While if you look only at one side, you get back anything Hawking entropy, and you're basically tracing down the left side. Is that the idea?
That's exactly the idea. Yeah.
Okay.
Exactly right. We're tracing out part of the system, so we're going to have some non-trivial, non-zero entropy. Yeah.
My question was the same, so it's good.
Same question. All right, so let me use my last few minutes to make one more remark. So now I'm going to use two boundary regions, so I'll call them A and B. So if we have A, so A and B are boundary subregions, and if A is a subset of B, then HA, the homology hypersurface of A, is going to be a subset of the homology hypersurface of B. And even though we haven't yet defined the entanglement wedge, this property turns out to be something that we call, and we'll define it later when we define the entanglement wedge, it's called entanglement wedge nesting. Now this particular phrasing of it is only really valid in static spacetimes, but that's what we're working with right now. So this is actually, I should say, this is really kind of crucial for many things that we do in AdS CFT and for reconstructability of the entanglement wedge. The proof of this is that is very trivial. So I'm going to show it in my last couple of minutes. So here we have, so here's my part of my asymptotic boundary. And here, let me use different colors. So this is my region A. Can you guys see that this is purple? Can you make that out? Yeah, okay, great. And let me call this larger region B. Suppose that this statement is false. So we're going to do this by contradiction. So we have some, so this is our Ryutake-Yanagi surface for A, and this is the one for B. So this is, we're doing this by contradiction. And I'm going to label the different portions of the surfaces. So I'm going to call this 1, this 2, this 3. 1 refers to this up to here, 2 refers to this portion, and 3 refers to this portion. And this is 4, 5, and 6. So 4 is this portion, 5 is this portion, 6 is this portion. So minimality, we know that this is the minimal area surface homologous to A. So minimality tells us that 1, this one, plus 2, plus 3 is less than 1 plus 5 plus 3. And you really had to go to TOSI to learn this particular bit of arithmetic. Now, we also have minimality for the B region. So we know that 4 plus 5 plus 6 is going to be less than 4 plus 2 plus 6. And here we appear to have regressed a little bit as far as our arithmetic goes, but you know, we're physicists, so math is not necessarily always our forte. But of course, these two are obviously contradicting one another, because one of these says that 2 is less than 5, and the other says that 5 is less than 2. And so we immediately say, oh, but that's, you know, that's a contradiction. And therefore, this cannot happen, which proves our statement. So we always have this nesting property. And this nesting property will turn out to be very valuable for us in the future. In particular, well, we'll need it to prove strong subadditivity for in a more general case for when we have time dependence, for example. And I think that maybe I will stop there. Next time we're going to pick up with strong subadditivity. And it's sort of a very similar type of proof where you kind of just label the different regions and you add them up and you do some arithmetic that perhaps sounds a bit wrong. And then you get a contradiction, which gives you a proof. So I think my time is up. So let me now take questions.
Perfect timing. Thank you. All right. Questions for Netta?
So the conclusion of this exercise is that 2 can be either less than 5 or 5 can be less than 2, right?
Exactly. Yeah.
Casey?
Hi. Yeah, I had a question. So could you go back to the page where you are defining the Ryutake-Yanagi formula?
Yes. I believe that's this one right here.
Yeah, and you have this thing. Okay, great. So
yeah,
the question was, suppose that chi-r is not a minimal surface, but everything else is true.
Okay.
But
so it's still homologous, just not locally, not a local minimum. Okay.
Exactly. It's not the local minimum, but it's everything else is still there. So how would you interpret the result that you find?
Well, certainly it would not have an S of rho r on this side over here.
Right.
In general, I think the question you're asking is quite interesting, which is what is the general information theoretic interpretation of the area of the surface?
Right.
And the short answer is we don't know. We don't know if there is one. Okay. If there is one, we don't know what it is. We might you could have reasons to think. So I would say that there's sort of two camps. People who say that there probably is one. People say probably isn't. I would certainly subscribe to the philosophy that there exists an information theoretic interpretation to a far larger class of surfaces than just the Ryuta-Yanagi surface. In particular, for example, the other local minima that are not global minima, but and potentially also the causal surface, although I don't know what that is. But I personally do not think that every surface has an information theoretic interpretation. But that you should keep in mind, that's my own personal perspective on this, and not one that has been established in any way.
Sure, of course. Thank you.
Mm-hmm. Other questions, discussion?
Yeah, I just have sort of a dumb one about remark 2 that you made. I couldn't see, maybe you can just explain a little more why for 2 boundaries you get this empty set?
Sure. So let's think about the two boundaries. What we need we're looking for the Ryuta-Yanagi surface of 2 boundaries. And so maybe actually let me bring back the Ryuta-Yanagi formula. And so we're looking for this chi-r, or this xr, which is the minimal area surface on a static slice, which is homologous to both boundaries. So homologous to both boundaries means that there exists a hypersurface, hr, or h, whose boundary is, maybe let me actually, I'm going to open a new page for this. So we are looking for a surface X such that there exists a hypersurface H where the boundary of H is given by X union, I'm going to call this S1 union S2, where S1 is, so this is the static Cauchy slice. Let's call it sigma 0, and S1 is the right boundary of sigma 0, and S2 is the left boundary of sigma 0. And so we're looking for a surface X where this is true. Now, if I just take X to be the empty set, then I'm looking for a hypersurface H where we're looking for H dot equals S1 union S2. But that's just sigma 0. So, we can say, okay, sigma 0 fits the bill, which tells us that the empty set is homologous to S1 union S2. And as soon as the empty set is homologous to our boundary region, it must be the minimal area surface, since its area is 0.
Okay, that makes sense.
The problem with the single boundary is that it's not true that the empty set is not in fact homologous to it.
Right.
Other short questions? Okay, so maybe we'll end the formal part of the questions, and let's thank Netta again. And if Netta, if you have time to hang around for a bit
Sure.
more.
Yeah.
Yeah.
So is it better if I unshare the screen for a more casual conversation, or people prefer the screen to be up so that I can write stuff down? I guess that's kind of up to the students.